Okay. Sweet. Sorry for the hair. All right. Oh man. Plugging in my computer real quick. All right. So this is going to be my video of showing the steps of doing the Anson's Fluent simulation project. So here we go. So first step, getting in this little Fluent Word toolbox. Just right here, this pops up. Go ahead and going to open up the design CAD section of it for the geometry. Since we're just doing flow over the plate, or flow over the cylinder, we're just going to make kind of our circle, and it's 2D, so it's going to make a circle, and then with our kind of our study area around it. So just following the tutorial video that Professor Osbe put out, just going to make circle and then 50 by 50 square, or yeah, 50 by 50 square in the middle, and then going from there. So I'm just going to do that real quick, and our dimension is, diameter is 1 meter, and total length of each side is going to be 50, and then to make it in the middle, 25 and 25. Sweet. I'm going to go ahead and make that an actual surface in order to go ahead and do our simulations on, and generate. There we are. And then with our 1 meter hole there, just to make it look a little bit nicer without any of the dimensions. There it is, our circle or cylinder we're going to be studying, and then our study area around it. All right, going on to the next step. Coming back to the initial, I'm going to go ahead and start with meshing. So just edit mesh. Wait for it to kind of pull up here. Here's our, here we go. So just gonna go ahead and start. Gonna make it triangles for the method. Go ahead and mesh. Here's our basic initial mesh. I'm gonna keep on adding. I'm gonna add the sizing for the cylinder. Gonna hit the edge to grab the edge of the circle or cylinder, and then element size 0.005. And behavior is soft. Can change soft to hard. Generate. And then we're going to also include the inflation. So that there, boundary is going to be the actual cylinder itself. Change the smooth transition of first layer. The initial height is 0.002. Minimum layer, maximum layer is 100. At the growth rate of 2.5. We're going to generate that mesh. There we go. And then we're going to change the overall element size. We're going to change that to 0.2. And then we can look at the total nodes and elements once that's done. It's taking its time. So I want to take this time. Oh, it's done. Never mind. I'm just going to say that fun, interesting project. Definitely wasn't the easiest to go ahead and grasp first time around. This is my first time using ANSYS or Fluent. So it was definitely fun, but definitely had its ups and downs. So now what I'm doing, I'm just gonna label our control area, control volume kind of thing. We're gonna write, the inlets, outlets, and then the walls themselves. So that was the first one, was that inlet, and then we're gonna make the back end the outlet, and then the top and bottom we are going to call them symmetry, but those are just the walls of the area itself. And then we're going to also name the middle. I'm going to just put that cylinder. Sweet. So I'm going to go ahead and look here. So one edge, that front edge, we got the 50 meters we put. Same thing on the back side, one edge, 50 meters. Symmetry is two edges, top and bottom, total of 100 meters. And then the cylinder wall itself is pi times the radius or diameter, which is 1. So 3.14, pi. So then going back, gonna go ahead and update our mesh, and now we're ready to go into the actual Fluent. Double precision. I add a few more solver processes, so just to make it a bit quicker. And then this is for that that first case, the inviscid flow. So just gonna go ahead and do that real quick. Add that here, viscous type. I'm gonna go ahead and put in viscid. There we go, and that should be that for models. Energy's off, everything else is off. Coming down to materials, this is where we identify our fluid. I'm gonna go ahead and keep it air. And then the density I did change to 1. This is gonna stay true for all my other cases. Won't go into that just in the sake of keeping this a nice short video. Surface body should be the same as what we specified in that first one. Yeah, 1 density, sweet. And then going to boundary layers. So inlet, this is where we want to identify our velocity speed. So 10 meters per second. And then outlet, we can go ahead and just make sure that it's 0. So gauge pressure is the same as the atmospheric pressure. There you are, 0. And then wall, since it's inviscid, we can't change any of the rotations or anything like that. It won't give us no options and so forth. But that's where I would change it for the upcoming cases. Yep. And then reference values, we're gonna go ahead and compute that from the velocity inlet. So changing the velocity 10, as we specified earlier, density is 1, and then everything else is kind of self-generated there. So coming to methods, scheme, simple, pressure, presto, gradient, least squares, cell space, and then momentum, second order upwind. Gonna go ahead and look at our residual, just make sure, yep, down to the thousandths, sweet. Do I close that? And then we're gonna initialize. Gonna go ahead and change that to 35 for the initialization iterations. And here we go. Sweet. So bottom here on the count, so you can see 35 done. And now we can go ahead and do our 1,000 iterations to actually solve. So this simulation part. And here it goes, seeing our residual, or yeah, residuals, the continuity keep going down, which is what we like to see. Once it gets to 10 to the -4th, it should converge, and we're getting closer and closer. Sorry for my my laptop noises here. It's a bit older, so it takes a toll on it to do all this. But it pulled through, so happy to hear. So we're just gonna wait for this to get ever so closer down to that 10 to the -4th. All right, it's gonna keep going. Just for the sake of my computer and just sake for keeping the video nice and short. We're gonna go ahead and end it here. Should help my computer. Sounds like it's about to take off. So to get our plots and contours, so first off contours here to get the pressure contour around the cylinder. We're gonna go ahead and select all of these and then save and display, or compute and then save and display, sorry. And then zooming in here, you can get the nice colors and graph. And then we're also gonna add another one for the velocity magnitude around the whole thing. Excuse me. So compute, save and display, and it shows this. Going back and forth between these two, that makes sense that there's a higher velocity on the top and bottom, and then the pressure is quite the opposite, where it's lower on the top and bottom compared to the two sides here. Kind of what we went through in class. So definitely super cool to see what's being learned in class being simulated here on the software. Really helps solidify that. And then coming down to the plots to see pressure coefficient around the cylinder. So this is going to be for the top half here. So direction vector and then 1. So, and there that is, just as we expected. Nice and curved. And then for our second plot, we're going to do the velocity distribution around the cylinder, only in the top half. Here we go. Yep. And it should be just like that. Since it is inviscid, there should be no wake behind it, so everything should be the same on both sides. All right. And then to get the lift and drag forces, so forces down here, x1, putting 1 in the x direction will be will give us the drag, and coming in here pretty close to 0, which is what we like. You know, we can't get exactly 0 in the simulation. It's not, you know, not perfect. So then going in the straight perpendicular direction, which would give us lift, and same thing, pretty close to 0. So just as we expect, where our lift and drag forces are 0 for the inviscid flow around a cylinder. To go ahead and get just a bit more the streamlines, and also a bit more colorful contours, going to the results page. And first off, I'll start off with the streamlines since we haven't done streamlines. Start from velocity inlet, so starting from here and going across. I like to put quite a bit of points, simply just to get a nice, colorful, not too spotty. It does take a bit of toll on the computer though. So, and there we are. So same thing as we saw in the Fluent side, higher velocity on top and bottom, which is what we expected. We can definitely pull up the contours. I'll show you the pressure contour here, which will be quite the opposite. So disable that. And so like I said, higher pressure on the sides here, on the front and back, not on the top and bottom, where the velocity is quite the opposite, where it is higher on top and bottom and lower on the sides. Show that right here. So there you are. So higher top and bottom, lower on the sides. So velocity and pressure. So see the difference there, and then streamline. And that's that. That is the project, and that's what I did for the first one in depth there. So going through the geometry of it, then the mesh, then the actual simulation, setting it all up, and then the results page. So, you know, contours, and then streamlines. And that's that. Sweet, thank you. And then went ahead and did it on paper for the Reynolds values of 150,000. Kept density the same as 1. Viscosity is 6.67 to the negative 10th and negative 5th. And then for the 800,000, viscosity is 1.25 10th to the negative 5th for density of 1. Sweet, thank you, and that's it.